An object has symmetry, or more correctly, mirror symmetry, if one half of that object is an exact reflection of the second half. An object can have symmetry in one, two, or all three directions. For example, Suzanne has symmetry along its x-axis only. If we use an imaginary blade aligned along Suzanne's local y and z axes to cut the monkey head in half, and then delete the left half, that missing half can be recreated by mirroring the remaining right half of the mesh. If we try a similar cut of the original with our imaginary blade aligned along the xy plane, deleting one half and mirroring the remaining half won't recreate the original mesh. Similarly, a cutting blade aligned along the xz plane can't recreate the original from only one half of the mesh. On the other hand, if we start with a cone, cutting along the yz plane or xz plane mirroring recreates the original. But a cut along the xy planes does not, so the cone has symmetry in two directions. Other primitives, such as the cube, sphere, or cylinder, have symmetry in all three directions. So why are we interested in symmetry when creating our models? The answer is simple. If the final model is symmetrical, we only have to model half the structure and then use the Symmetry tool to create the second half. The Symmetrize tool in Blender's Mesh menu allows us to automatically mirror a mesh along a specified axis to produce a symmetrical mesh. To demonstrate, we'll start with a UV sphere, enter Edit mode, and delete one half. With proportional editing switched on, we'll pull out a few vertices to create limbs on the mesh. Only the selected elements will be mirrored, so we'll select all parts of the mesh by pressing A and then perform the Symmetrize operation to create the second half of the mesh. The last op panel's Direction field allows us to select the direction of the mirroring. In our case, we want to mirror the elements on the positive side of the x-axis to the negative side of the x-axis. Vertices that have an x-coordinate value of 0, that is, vertices right on the position of our imaginary mirror, are not copied since that would just create a duplicate vertex in exactly the same position as the original. The second parameter, Threshold, allows us to introduce a little leeway to the positioning of the vertices that have an x value close to 0. Vertices within the threshold value are repositioned to give them an x-coordinate value of 0 and not duplicated. When using the slider to set this value, Blender restricts the value to the range 0 to 0.1, but we can type in larger values, which is usually a bad idea. In fact, the very first step in the example we just worked through isn't really necessary. We don't need to delete one half of the original mesh before we start modeling. The Symmetrize operation will automatically do that job for us. Another point to note is that the Symmetrize tool uses the local axes set when performing its calculations. This means that even if we've rotated our object before creating the other half of our model, the results are still correct. Of course, in the real world, few objects have perfect symmetry. For example, although us humans may look reasonably symmetrical, there are always some differences between our left and right sides. If such differences are to be incorporated into our model, we can always make adjustments after the Symmetrize operation has been performed. The Snap to Symmetry tool is used, not to create symmetry, but to ensure that an existing mesh is perfectly symmetrical along a specified axis. While biological bodies are never truly symmetrical, man-made objects such as buildings and car shells are usually perfectly symmetrical, at least at the design stage. The Snap to Symmetry tool adjusts the position of individual vertices to create perfect symmetry in the given direction. To demonstrate, We'll use the tool to return our model to perfect symmetry. After selecting all the elements of the mesh, we'll apply Snap to Symmetry. For the moment, there's no change. The two sides are obviously not symmetrical, with the left horn much larger than the right one. If we look at the last op panel, we'll see the reason for this. First, we have the direction field, which specifies the direction to adjust for symmetry. Here we want +x to -x. Next is threshold. This determines how big a difference between the two sides the operation is willing to correct. If we've made a really large change between the left and right sides, Blender won't try to correct it. And because the left horn's top vertex is significantly further away from its neighbors than the equivalent vertex on the right-hand side, Blender has not performed any correction. If we increase the threshold value, then the difference will be corrected. The parameter factor determines how the correction is made. With a value of 0, the right side will be made to match the left side, assuming we have selected +x to -x. But if we increase this value to 0.5, then both sides are adjusted to the average between the two vertices being moved. Using a value of 1.0, the left side will match the right side. Finally, Center snaps any vertices that are slightly off-center to the center position. In other words, these vertices are given an x-coordinate of 0 in this example.